Hey everyone, I got some requests to talk about the idea of figuring out your bounds when you're working with converting to a different coordinate system, particularly in the context of setting up an integral. So I wanted to spend some time going over a few examples of how to do this, some of them a little bit trickier than the ones that we've looked at previously. Okay, so before we launch into this, I want to kind of explain how this fits into setting up an integral. So when we're looking at an integral and we want to move it to a different coordinate system, there are three parts that we have to consider. So an integral, I'm just going to use a triple integral, for example, but this applies with double and single integrals as well. So if we have integral over some region omega, and we have everything in Cartesian coordinates like so, there are three pieces here we have to think about when we want to change coordinate systems or move over to a different parameterization or something like that. And those are the bounds that come from omega, the actual function itself on the inside of the integral, and then we also have to consider what needs to happen with the differential. And this video in particular is going to focus on setting up bounds. In particular, converting regions from one coordinate system to another. And then I'm also going to briefly mention differentials at the end of each example. So anyway, the big thing here, though, to point out is that when we're looking for the bounds on our omega, I mean, we start with some region, and then we want to change over to a different coordinate system. So all of our examples are going to be, we're given a region, we just need to change coordinate systems, okay? So we're just going to isolate that one part of setting up the integral. Okay. So let's go ahead and launch in with some examples. So in our first example here, we're going to have a triple integral over a region R of some function f, x, y, z, dv. And we're going to convert our region R into a different coordinate system. So R is going to be equal to x, y, z, such that the square root of x squared plus y squared less than or equal to z less than or equal to 3. And we have that x is less than or equal to 0. Okay. So we're really just going to focus in on converting this region. And we're not going to worry too terribly much about what that function is there on the inside. And we're just going to look at what needs to happen with the region here. So we're going to kind of sketch the region. So there's our goal. Okay, so if we look at this region here, we've got this shape right here is a cone. And since it is less than or equal to z, we know that we want the inside of the cone. And we know that it's less than or equal to 3. So that means that we have a flat top. Okay, so we want to cut off our cone at z equal to 3. So it's going to look something kind of like that. So that's the region that we are looking at. And in particular, we want x to be less than or equal to 0, and that occurs back over here. So we're looking at kind of the back half of this cone right here, something kind of like this. So we want this region in particular. Okay, maybe a darker paint would be better. Okay, there. So this is the part that we want. So how do we write this in a different coordinate system? What other coordinate system should we use? Well, since we're looking at a cone that has a flat top, And since we've got this kind of like x squared and y squared and z is just left alone, our best bet is going to be to use cylindrical coordinates. So we're going to be looking to set up our region in terms of r, theta, and z. And so we just need to come up with the bounds on each of those. I'm going to label all my axes first. Okay, so let's look at r. So we know that if we look at this expression right here and we think about our cylindrical coordinates, we know that r squared is equal to x squared plus y squared, which means that this guy right here, this square root x squared plus y squared, less than or equal to z, less than or equal to 3, is going to become r less than or equal to z, less than or equal to 3. We also know that we always want r to be greater than or equal to 0. So if we ignore the z here momentarily, we know that we need r to be between 0 and 3. Okay, so those are our bounds on r. Next up is going to be theta, which we use considering what kinds of restrictions we have on x and y. So in particular, theta or x is supposed to be less than or equal to 0. So we're looking at this part back here of the xy values. And this ranges from, if we start here at 0, we have pi over 2, and then we have pi, and then we have 3 pi over 2. So in this particular instance, we are looking at theta going between pi over 2 and 3 pi over 2. And finally, that brings us to looking for restrictions on z. So looking at this guy right here, we already said that r has to be between 0 and 3. But now we want to keep z being controlled by what r is. So z has to be between r and 3. And yeah, so that's really pretty much it. So this would give us the bounds for our new system right here. And so now keeping this in mind, we can set up a new integral, converting this over. And what you would get then is the integral from, say, we could do pi over 2 to 3 pi over 2, and then integral from 0 to 3 for r, and then integral from r to 3 for z. Notice that since there's an r here, this guy has to be on the inside of any integral with respect to r. You convert your function over. So you may have to do some substitutions in here using the identities for x and y. And then you would add in the r, and then dz has to be first because we have an r here in this bound of integration, followed by dr d theta. Really, these two can be in any order as long as dz occurs before dr, so that way it takes care of this r here in your bounds. You want to make sure that your outside bounds here have absolutely no variables in them at all. Otherwise, you'll wind up with some kind of weird values at the end because you won't have gotten rid of all your variables. So yeah, this guy right here, this goes back to the idea of these were our bounds. This is our converted function. And then don't forget that here, this swaps over our differential. And please, please, please do not forget that this pops up with the cylindrical coordinates. So we add that extra r in. It's kind of the same idea as how you get some extra terms that pop up when you do u sub as part of what's called change of variables. Do not forget it. It's a very, very easy way to not lose points on an exam is to make sure that you have that particular piece right there. Same idea is like, you lose points over plus C in Calc 1. Well, this is kind of the equivalent here. When you swap over to cylindrical coordinates, make sure you have that R there so you're not losing some easy points. Anytime that you change coordinate systems, something like that's going to pop up. For cylindrical coordinates, it is just that R. Okay. So let's look at spherical coordinates then and see what those kinds of problems look like. So in this example here, we're going to do another triple integral over some region R of some generic function f(x,y,z) dv, where our region is equal to x, y, z, such that x squared plus y squared plus z squared is less than or equal to 49. And then we have x greater than or equal to 0 and y greater than or equal to 0. Okay, so if we kind of sketch this, first and foremost, so this right here describes a sphere of radius 7. So let's draw a sphere. I claim that that has radius 7. And then we want the part where x is greater than or equal to 0 and y is greater than or equal to 0. So that's going to give us this piece here and this piece here. And there is no such restriction on z, which means that we're taking the entire length of it up and down like so. So we're looking at kind of like a quarter of it like so. Think about like I don't know, a slice of a pickle or something is kind of what this winds up looking like. Just like that. So we have kind of like this quarter of the sphere. And since we have that, we're going to want to use spherical coordinates. So what we're going to shoot for is to write r in terms of rho, theta, and phi. So we're going to look at this to get the information we need about each of those. Right here, this is the really easy one. We'll have rho squared less than or equal to 49, which means that rho has to be between 0 and 7, like so. Okay. All right, so now we have to worry about theta. And since we are working entirely in kind of like this piece right here, I want theta to be between 0 and pi over 2, just like so. I just want this little quarter right there. And then finally, we need something for phi. And phi is kind of like, it's just this little angle right here. Okay, I'm going to extend this out so you can kind of see what I'm looking at. So it's this angle right here between the z-axis and whatever spot it is that you are on your little sphere there. And we want it to start up here at 0 and be able to sweep all the way down to the negative part of the z-axis, and that's going to take me down to pi because it's a half circle. So phi is always ranging between 0 and pi. It's just a matter of whether we want to put further restrictions on that. In this case, we don't, because we want this entire slice right here from top all the way down to the bottom of it. So phi is allowed to take on its full range of motion. And I do want to emphasize that phi will never be negative. It will never be greater than pi. It is always something between 0 and pi. I mean, it could be pi over 4 to pi over 2 or something like that, or pi over 3 to pi over 6, or, you know, something, I don't know, that's a little bit backwards. But it's always going to be some values that land between these two right here, because anytime that we want to go ahead and get like the back half of our sphere, all we do is take theta and send it over that direction. Okay, there's no need to make phi flip over backwards or anything like that to make this arm reach around back over on this side. It is sufficient for it to just stay between 0 and pi and not have to arc back over there. So something to keep in mind. Anyway, to recap, 0 less than or equal to theta less than or equal to pi over 2, and phi is between 0 and pi in this case. And I will say, generally speaking, if you don't have a restriction on z, whether it's positive or negative or anything like that, and you're really just looking at like a z-squared type thing right there, generally speaking, you're going to be looking at phi being able to go from 0 to pi. So yeah, that's pretty much restructuring this region right here. Now, if we wanted to look at our new integral to set that up, what you're going to get is integral from 0 to pi, integral from 0 to pi over 2, integral from 0 to 7 of whatever our new function is, because you got to convert this guy over. And then your differential and the extra multiplier that you get in this case is rho squared sine of phi. D rho corresponds with that one. Looks like we're going to do d theta next, and then d phi. So again, we've got our bounds that we've swapped. Don't forget to also convert the function. And then the differential. Okay, so once again, just like on the last one, we want to make sure to not forget this extra multiplier thing that we've got in here. This is the one for spherical coordinates. Okay, so it just automatically gets multiplied in. There's not really anything that changes about this. Anytime that you use spherical coordinates in an integral, this should make an appearance. So every time. Okay, I've got two more examples for you that are a little bit on the trickier side, because those two were fairly straightforward in as far as what the shapes looked like and stuff like that. But I wanted to make sure to look at a couple that were more complicated. So in this one, we're going to do a triple integral over some region R of f, x, y, z, dv. And then our region R is going to be equal to the set x, y, z such that 36 is less than or equal to x squared plus y squared plus z squared, less than or equal to 144. And then we also have that z is less than or equal to the square root of x squared plus y squared. And then it's in the first octant. Okay. So let's try to sketch this thing. I have a feeling that this one's going to wind up being a little bit messy, but we'll see what we get out of it. Okay, so we've got these two inequalities right here. Best way to approach this is to just do one at a time. So the first thing we note is that we want a sphere of radius 6, and we want to be on the outside of that sphere due to that inequality right there. So here is our, this will be our sphere of radius 6, like so. And we want to be on the outside of that, so I'll just draw some little arrows to point that we want the outside. Okay. And then we also need it to be inside a sphere of radius 12. So here's our sphere of radius 12. Like so. Already we're getting to be a little bit on the messy side. And we want the inside of this sphere right here. So already we're looking at kind of like this shell type thing. It's, you know, hollowed out on the inside. You can think of like a, I don't know, like a tennis ball or something like that, where you really just want the shell of the tennis ball. So it is definitely solid between those two, but we just want the layers between those two spheres and not necessarily the entire inside of the large sphere, the entire outside of the smaller sphere. Okay, so that's our first restriction. The next thing we want to look at is this cone thing we've got going on here. I'll draw this in a different color. So we know that we want some sort of cone shape like so. And we've worked with cone shapes before, right? Because that kind of adds this kind of deal right here. Okay, so I mean, maybe we're looking at this little plug piece looking at the top, except we've got this inequality right here, which tells me that I actually want the underneath side of the cone because I want my values of z to be smaller than what's inside of the cone. So I'm going to draw more little arrows to denote that I want kind of the underside of that cone. Okay. And finally, we are told that we are in the first octant. So we're looking at stuff that lies in this segment right here, where x and y are greater than 0. So to kind of conclude this, I want the piece that's underneath the cone and yet in between my two spheres. So it's going to look something kind of like this. It's just going to be like a little chunk of, let's see if I can kind of draw this a little bit. something kind of like this. It's going to be a little curved piece out of the sphere. It's going to look something kind of like that. So it's almost like a rectangle that got a little bit squished. So it just kind of fits nicely right in there. So this is the idea of the shape. Obviously, this picture is a little bit messy, but hopefully it will still be somewhat helpful in identifying our bounds. So our goal here, since this is just a little chunk of a couple of spheres here, we're going to use spherical coordinates. So we're shooting to get rho, theta, and phi out of this. So our restrictions are on rho are once again probably the most straightforward part. We're looking at 36 less than or equal to rho squared less than or equal to 144. So 6 has to be less than or equal to rho, and then that has to be less than or equal to 12. Okay. Now, if we look at theta, since we're in the first octants, I mean, a general rule of thumb, if you're in the first octants, theta starts here at 0, and it's going to go up to, well, pi over 2, okay? Because we still have this is our x-axis, that's our y-axis. So anytime you're in the first octant, theta is typically going to be between 0 and pi over 2. All right, and then finally we have to worry with phi. So I already used orange, so I should probably use, let's use purple. Okay, so phi is measuring how much it's moving in this direction, up and down like that. So it kind of starts right here, and I need it to sweep downward like so until it hits the xy plane. Well, the xy plane piece, that's the easy part. That's pi over 2, okay? So it's going to sweep down until it hits pi over 2, and then there it has to stop. So where does it start at? Well, it starts at the outside of this cone. And the cones generally have sides that slope at 45-degree angles, or pi over 4. So its starting point here is going to be pi over 4. So I want it to be able to, my little arm here has to be able to start here at pi over 4 and then be able to reach all the way down to my xy plane. So we have pi over 4 less than or equal to phi less than or equal to pi over 2. Okay, and that's it. I mean, like, it looked really messy. The big thing is just try to take it one piece at a time. And yeah, so, okay. So let's go ahead and convert our integral over. The new integral will look something kind of like this. We'll have an integral from pi over 4 to pi over 2, integral from 0 to pi over 2, integral from 6 to 12 of whatever our converted function is. Don't forget that. And then we have our multiplier, rho squared sine of phi. And then we have a, this is going to be d phi, d rho, d theta, d phi, just like that. So that's what our new integral would look like. Okay. Yeah, so that's pretty much it for that one with the spherical coordinates. And then I've got one more for you. So for this one, triple integral over a region R, f, x, y, z, dv, where the region is equal to x, y, z, such that x is greater than or equal to 0, y is greater than or equal to 0. And then we have negative y has to be less than or equal to z less than or equal to x squared plus y squared. And then finally, we also want x squared plus y squared to be less than or equal to 25. Okay. So I'm going to tell you right now that this is a really tough one to sketch. Anytime you have some kind of linear things going on here mixed with some squared things, it's going to be really tough to draw. So my preference when I run into things that I already know that drawing it isn't going to get me anywhere, it's not enlightening at all, which again, you can kind of tell because we've mixed linear terms or things that don't have squares on them with things that do have squares on them. So we're looking at a plane that's crossing some sort of cone. Tough to sketch, but we can approach this very algebraically. So this is difficult to sketch. So we will approach it algebraically. And what do I mean by that? Well, I really just mean that we're going to take what substitutions we know and we're going to plug them in. Well, so the question then becomes, though, how do we know what substitutions to use? Because, I mean, we haven't sketched the region. We don't know what it looks like. Well, since we have just a plain z here and the just x squared and just y squared, no z squared here, we are going to use cylindrical coordinates. Okay, so now we've identified that we're going to use cylindrical coordinates. And anytime that we have cylindrical coordinates, we know that x is equal to r cosine of theta, y is equal to r sine of theta, z is just equal to itself, which is why when you have z by itself there, cylindrical coordinates are a great idea. And we know that x squared plus y squared is equal to r squared. So there's actually a lot of stuff we can do here without ever drawing our region, because this means that our negative y less than or equal to z less than or equal to x squared plus y squared has to become, well, the negative y becomes negative r sine of theta less than or equal to z less than or equal to r squared. Well, now we have bounds on r, or on z. The only difference is that we have to be careful when we set up our integral and like what order we integrate in. So that is totally fine. This piece right here, the x squared plus y squared less than or equal to 25, that just means that r has to be less than or equal to 5. And we always know that it's greater than or equal to 0. So at this point, the only thing that we're really missing is going to be theta. So how do we figure out theta? Well, we don't have to sketch the whole region to figure this piece out. We already know that we're looking at x to be greater than or equal to 0 and y to be greater than or equal to 0. So we're looking at this corner right here. So I need theta to fit right in there. And that means that theta has to go between 0 and pi over 2. Did not have to sketch the region to figure that out. All I know is this is the restriction I have on x and y, and theta is what gives me restrictions on x and y. So my new region is going to be 0 less than or equal to r less than or equal to 5, 0 less than or equal to theta less than or equal to pi over 2, and then finally negative r sine theta less than or equal to z less than or equal to r squared. Which means that my new integral is going to be from 0 to 5, 0 to pi over 2, and then negative r sine of theta to r squared of whatever my converted function is. So swap everything over to r, theta, and z for whatever's inside of here. And then we multiply by r, and then we integrate with respect to z first, and then d theta dr. It is very, very important that you make sure that this r squared and r sine theta is on the inside here, because otherwise they won't be gone completely by the time you finish integrating. So yeah, that's just kind of an approach. If you get really, really stuck on how to sketch the region, if you're having a lot of problems with it, especially when you've got this mix of linear and not linear terms, you can always attempt to approach it algebraically and just see what shakes out. So some strategies then that we've kind of noticed today. Okay, first one, sketch the region. That one goes without, I mean, like I've said that a lot at this point. Sketch pictures, do whatever kind of drawings that you can. Now, I've gotten a lot of questions about how do I sketch the region? How do I make my drawing not look just abysmal or, you know, terribly so messy that you're not able to read it? Well, one option is you can dramatize shapes. So, for example, a cylinder, or not a cylinder, a cone can be drawn with steep sides. So that way, because I know one thing that people complain about is, okay, my cone gets tangled up with my y-axis there. Well, just draw the cone to have steeper sides. Keep in mind that this is actually pi over 4, but now that the sides are steeper, it's not dealing with y. So just remember numerically what it actually has to be, but don't be afraid to draw things that are a little dramatic. The other thing that you can do is use lots of colors. Okay, there is a reason that I color code a lot of my pictures, right? Like if I had drawn this entirely in black, you would not be able to read what was going on there. So don't be afraid to use a different color, to go ahead and sketch your region in a lighter color and then shade in the one that you want with a darker color, and then use a different color for each variable that you're trying to pick out. Just lots of colors. Use all the colors that you want. Don't be afraid to use colors, okay? So combining these two strategies right here will immediately make your drawings a lot easier to interpret. The other thing, though, is that if you can't sketch your region, like we just saw in our last example, is don't be afraid to just use the identities to plug and chug. So this is a very algebraic approach. You're just saying, okay, I trust that these identities are correct. So again, that was kind of like that example where we swapped out the y for the arc sine theta and all that stuff, without ever really drawing the picture. And that's okay. That is totally okay. You get really stumped, you don't know how to draw it, or the drawing is just simply not going to be helpful. Do not be afraid to try to reason through it algebraically, or even just draw like certain pieces of it. Again, like we did here, we said, okay, well, theta, I really do maybe need to see a picture of that. Well, just draw that one restriction that gives you the information about theta. So another strategy then is to isolate corresponding pieces of information with their restrictions. Or pieces of information with their conversions, I guess, right? So theta corresponds to x and y. So we really only needed the information about x and y to be able to make that kind of restriction there. So, okay, anyway, I hope this was helpful. A lot of examples there, and maybe that cleared some things up for you.